Continuing with the planet Mercury, I thought I could fit this in the first lecture, but it's a little too much to talk about. We left off talking about the fact, first of all, that usually when one object dominates the other, like our Earth and our moon, the Earth dominates the moon so much gravitationally that the same side of the moon always faces the Earth. It's called being tidally locked. You would assume that Mercury then would be, perhaps tidally locked with the sun. That's what astronomers assumed right up until 1965, and they were bouncing some radar off with Arecibo, the big Arecibo dish in Puerto Rico, and they noticed, Mercury does spin very slowly, but it spins on its axis. So that just the fact that it spins at all, kind of independently, let's say, of the sun, is a bit of a surprise. Now, again, it's a very slow spin. But they think that perhaps the fact that it's not a very circular orbit, it's a little more eccentric, a little more stretched out elliptical orbit than most of the planets, and that might have prevented it from becoming tidally locked. So that's how the physics on that apparently worked out. When I say a slow spin, I mean Mercury spins one time in the time that 2 months have gone by on the Earth. So that's a pretty darn slow spin, especially when you consider that Mercury only takes 88 days to orbit the sun. That's its year, 88 days long. And so we call that a 3-to-2 spin orbit resonance. It turns out that Mercury spins 3 times on its axis in 2 years, in 2 orbits. Now, here's where things get complicated. All right? Spinning on your axis is called a sidereal day. But we base days on where the sun is at in the sky, like, let's say, from noon to noon. Right? That's called a solar day. Well, it turns out that a solar day on Mercury is actually 2 years long. Mercury has orbited the sun twice. So let's say it's noon and you're having lunch with your friend on Mercury and say, hey, I'll meet you tomorrow at noon for lunch again. You're going to wait 2 Mercury years for that lunch to happen. Now, this gets kind of hard to explain, but basically if you're where the pink dot is, let me try my best here real quick. On the right, let's say you're right here, you're at the pink dot, the sun's above your head, it's noon. You're spinning so slowly by the time Mercury comes back around, 1 year has gone by, right? You've made an entire orbit around the sun. Look where the pink dot is now. The pink dot is facing directly away from the sun. That's called midnight. So think about it. In 1 whole year, you've only gone from noon to midnight. So that's half a day. Guess what? Now to go from midnight back to noon, the next noon, is going to take another whole year, another whole loop around the sun. So 2 years go by before 1 day goes by. So for my students, and here's a little more complicated explanation, sometimes I go through this in class, and sometimes I spare my students the boredom of going through it. But anyway, here's how to remember it. 3, 2, 1. It's as easy as 3, 2, 1. 3 spins on the axis every 2 years makes 1 day on Mercury. Kind of interesting. All right, some other little tidbits here. One little piece of trivia. Mercury is the only planet that does not tilt on an axis. All the other planets, as they're going around the sun like this, right? They're tilted like so. So the Earth is tilted as it goes around the sun by 23.5 degrees. Mercury, straight up like this and goes around and around, which means, as you remember, our seasons are caused by the tilt. So there are no seasons on Mercury. Not that it really needs seasons. It's, 800 degrees in the daytime and negative 200 something at night. So, anyway, it still has extreme temperature differences, but it doesn't technically have seasons because it has no tilt. And finally, my favorite thing. So we've had some surprises. I started out kind of putting Mercury down because it's such a poor, backyard telescope type object. But it's had some surprises, right? It had a magnetic field that they didn't expect. It can cross in front of the sun. It can make a transit of the sun, which is kind of cool. But my favorite part of Mercury is the fact that it played a role in one of the greatest scientific discoveries of all time. You see, by the late 1800s, astronomers began to realize that Mercury's orbit was not really behaving well according to Newton's laws. Now, that's not right. Physics is, supposed to be universal. And at first, it just seemed like this little bitty problem, like a little crack there and nobody knew that the whole dam was about to burst. And it was about to lead to a whole new theory. So Mercury's orbit doesn't exactly obey Newton's laws. If you just plug into Kepler's third law or whatever, you're going to be off by a tiny amount. And that's because Mercury, again, is closer to the sun than the other planets. And so it took a different set of equations to explain its orbit. It does something very interesting. If you look down at the bottom right, its entire orbit precesses, it turns around the sun over time. Newton's laws don't predict that at all. But somebody came along that could explain it perfectly. And that somebody was a guy named Albert Einstein. So Albert Einstein, his theory of gravity, the way that he proved his theory was on the right track was by being able to explain the precession, the rotation of Mercury's orbit where Newton's laws failed. That was it. So imagine that little Mercury, its orbit, can only be explained, perfectly with the laws of the relativity laws. So relativity equation. So it's pretty cool that little Mercury played a role in one of the great scientific discoveries of all time. And I think that's about it for Mercury. Thanks for listening.